Now, we will go for the electromyography or EMG signal. We told about the motor neurons. Those motor neurons, they are actions, they terminate on the muscle fibers, and whenever a signal comes, that it actually stimulates that muscle, and the muscle in response it contracts, and that is what we call as twitch. And for a single motor neuron, it is not connected to one muscle fiber, but a number of them. So, we call that collection, all those fibers together, as a motor unit, and the action potential generated by that we call as motor unit action potential. So, that means the signal given by a motor neuron, it is stimulating some actually fibers connected to it, and the potential generated by the action potential of all those muscles or muscle fibers, that is motor unit action potential. And for a task, they are actually engaged again and again. That means, to lift an object, say lift a heavy bag, we need to ask our muscles of the arm or excite the muscles of the arm again and again to exert that force. So, that is done by train of stimulus that is coming through the motor neuron. So, the summation of them, that the motor unit action potential train, in short we call as MUAPT, and a single motor unit, it can be connected to a very small like 25 muscle fiber up to 2000 muscle fibers. And if we look into the weight of it, it could be 0.1 gram to 250 gram of weight. So, depending on the span of that connection, that a varied number of actually muscle fibers can be excited by one motor neuron, and the signal generated by that contraction or depolarization and repolarization of the muscles, we can get the signal what is called as EMG. So, now let us move forward, let us see that how the signal looks like. Here we are showing some of the signals. Here what is shown, that usually we collect the signal from the skin, and there we will not be able to get the signal from a particular motor unit. The multiple motor units, the signals, they would be combined together and we get the combined signals. So, the combined signal will look like a little busy one, but if we could decompose them, we could get them separately having their own characteristics. Now, how these signals are connected? First is through the surface electrode, and usually that the diameter of that electrode is 0.5 to 2.5 centimeter. So, it could be very small up to about an inch dia. So, these are patch electrodes. Now, if we want to pinpoint and want to collect that more specific information, then we need to go for needle or wire kind of connections. The typical actually cross section of it is about 1 square millimeter, and there could be different kind of needles. It could be monopolar, where the needle is connected to one wire, or it could be concentric, that means two connections are there, one from the sheath, another going through inside. So, we can get very localized activity within this region. Then it could be a single fiber also, and it could be going through a actually pipe shaped needle. It could be just placed inside just to protect it and to help it to reach that space from where we want to collect the signal. So, there are different types of electrode, and depending on their activities, that we will get different kind of signals. And here in case of EMG, another thing we should look at, that the signal strength again is again small in microvolt range as we show it here, but the frequency is much higher. For both ECG and EEG, the frequency range was below 100 hertz. In this case, it is starting from 5 hertz to 2 kilohertz. So, frequency band is much bigger, and the signal looks more like a noise signal, or we can say just like the EEG signal. Here also we cannot get any shape, rather we have to look at that signal which is looks like a random signal and try to analyze that or quantify that signal. Next, we look at that how we can perceive this kind of signal or quantify this kind of signal. That signal here is fed to a differential amplifier to enhance the level of the signal, so that it can drive some other electrical equipment, and after using the power amplifier, the signal can be boosted and can drive a speaker. So, in this mode, what we are interested in, from that EMG signal we are generating a sound. So, if the muscle activity takes place, for example, the person is lifting that weight, and there would be some muscle contraction would be there, and we have connected the electrodes on those muscles, and that is fed to the speaker using the different sets of amplifier. We can get some sound that is due to the EMG signal output. Now, at the level of the sound, we can get that how much actually EMG signal is generated. If the muscles they are not working properly, that level of the signal will go down. So, that can give us an indication about the amount of EMG signal generated or the health of that muscle. The next thing, that after the differential amplifier, a tape recorder may be used to record that signal for future use. For example, if some patient is under treatment, so and he has given different kind of treatments like medicine, physiotherapy and all. So, we want to see that for the same experiment, what is the improvement in the muscle strength. So, we need to record the previous signal and the present signal and need to play them one after another to perceive the difference or the improvement in after the treatment. The other mode of actually judging that is whatever the signal we get, we give it to the CRO after rectification and integration. This rectification and integration will provide us the envelope of the signal. Later on we will get more details what we mean by the envelope, but at this point you can take it in this way that it will give us the level of the signal, and that we can visualize in a CRO. And when we look at the CRO, we are able to get the change of the strength of the signal over the time. So, it gives us more information about the signal. So, that is another mode of visualizing the EMG signal or EMG recordings. Now, let us look at some application of this EMG. That here when we have this kind of problem, that the person finds that the muscles are not working, actually two things can happen. One thing, there could be a disease of the muscle. So, that is called as myopathy, that muscles or the muscle fibers are getting degenerated. Other thing could be that muscles are healthy, but there is some problem in the electrical connection to the muscles, which is actually stimulating the muscle. In other words, the neurons that is activating the muscles have some problem. So, in that case it is called as neuropathy. So, when we have some problem of the muscles, that would be the complaint from the patient, or that can be immediately visualized. The first thing is to find it out that whether it is a problem of myopathy or it is a problem of neuropathy. That means, the muscles are diseased or the neurons are having some disease, because unless we know that, the treatment planning cannot be done. So, to check that, what it is done, that we put that sensor at different parts of the body. Now, to do that, we need to know that how the nerves are laid in the body. So, that knowledge is required. Here the problem is in the leg muscle. So, the 2 points from there, that in that nerve, that about a half a meter apart, 2 sensors are connected, and the signals are actually tapped from or acquired from these 2 points. Now, first the signal will come here and then to the next point. So, here what we look at, what is the time difference between these two, and thereby we can get actually that what is the velocity of the signal through that nerves. And we know the normal actually speed should be 50 to 60 meter per second. If it becomes much lower, that means we know that nerve is not conducting properly. So, the problem is with the nerve, and we need to do the treatment of the nerves. If the speed is fine, then we get the nerves are working fine, they are giving the stimulus as the way it should give, but the muscles are not responding to it. That means, the muscles have become weak. So, For that we need to have the treatment of the muscles, so that the muscle fibers can get regenerated and regain their strength. Now, we can look at actually more such signals which can be acquired from the body. First, we look at the electroneurogram. The electrical signal which acts as a stimulus to the muscle, and the nerves carrying them, and it is passing through the nerve, taking the command or taking the signal from the sense organ to the central nervous system. We can look at the velocity of that, and if we do the recording over the length of it, that signal is called electroneurogram. That is called as electroneurogram, or in short ENG signal. In the previous page, we actually depicted one example. For the neuropathy, we have to take that electroneurogram. The next signal is event related potential. Event related potential means if there is any stimulus, in response to that, whatever the signal is generated, we can call it as event related potential, and that is why it has another name called evoked potential. And where we can get the event related potential or ERP, we can get that in EEG or ENG. For example, if some stimulus is given in the form of light or sound or some electrical signal or even the touch, that can actually give rise to some change in the signal we are looking at, that is EEG or ENG. As it is evoked or related to that particular event, we call it as event related potential or ERP. Next, we can look at gastogram. Electrogastogram is the electrical signal of the stomach and actually that alimentary canal. We know the peristalsis is happening, which is nothing but some rhythmic movement or rhythmic contraction. The contraction and expansions are synchronized in such a way that the food will move in one direction, so that muscle movement and the command to them, they together form a signal which can be captured from the alimentary canal throughout, including the stomach, and that particular kind of muscle signal, again you can tell that is also a variant of EMG, they are called as electrogastogram. Okay. So, it can tell us that how the muscles in our alimentary canal they are working and how they are helping us for the digestion. If they become weak, then we may have the problem of digestion. Next, we get another signal called phonocardiogram. Phonocardiogram is the signal of the heart and the connected vessels. We know heart is a pump, and when the pump is working, that there is actually transfer of fluid, that is the blood, from one chamber to the other, and there are number of valves. If the valves are not operating properly, or that the transfer is not smooth, it can give rise to some signal. In the same way, when they are actually forced through the artery, it gives rise to some turbulent motion, and it can create some sound or vibration. And if that is captured, that's called phonocardiogram. In fact, this PCG signal is a very good source of information about the health of the heart, and you can collect that in a non-invasive way. Now, what kind of information could come, or how this vibration is generated? Think of the valves, they are actually having some calcium deposition. So, if there is calcification of the valves, then instead of making a smooth landing, it will make a metallic sound. Whenever it is closing, it will make a metallic sound. So, that will bring some change in the PCG signal. Again, because of the calcification or some slackness of the valve, if they are not closing the valve properly when it is supposed to close, what will happen? That there would be some leakage, and because of this leakage, the leakage would be small. So, when that chamber is actually getting contracted, say the ventricles are getting contracted, and because of leakage some blood is again flowing back to the artery. So, in an atrium, so where it is supposed to go through the ventricles, that can give some hissing sound. So, we would look at that signal, and that would actually can give us some indication that there is some leakage of some of the valve, and it is creating some problem. Again, the main arteries, they are taking the blood, carrying the blood. If they becomes narrow because of deposition of that lipid, or because of calcification, then there would be a highly turbulent flow, and that will also cause sound very near the heart. So, that will also be captured as PCG signal, and that is why we call that it is a cardiohemic system, that heart and the blood together, that makes this sound, and that is captured in phonocardiogram. And now, let us look at another similar signal called carotid pulse signal. We know that carotid artery, it carries the blood from the heart to our brain. It is the main supply line of the blood to the brain, and brain is one of the biggest consumer of the blood. It needs a lot of blood to keep it alive and do all the activities. Now, this main artery, it flows very near the skin, and just like we can actually get the pulse near our wrist, same way very near to our that neck there are some points, if we touch that we can get actually feel the pulse there. And we know that what is pulse? When we have the systolic pressure, then we get a thrust and we can feel that as a pulse. So, if that signal is collected from that carotid artery, it is called carotid pulse. And when there is that high pressure of the systolic pressure is actually changed, that means the ventricles they stop the contraction and start relaxing. There is a momentary dip in the pressure, again as the valves are closed, that the pressure maintains and we get the pressure as that diastolic pressure, and that helps to maintain the unidirectional flow of the blood. So, that changeover point also we can get in the carotid pulse signal, and that can act actually as an indicator of the activity of our heart. So, this is all about an introduction of different kind of that biomedical signals. Thank you.